So here we go. We're going to revisit the Atwood's machine. Oops. There we go. The Atwood's machine again, but this time from a work and energy perspective. All right, so we have two main ways of dealing with this from a work and energy perspective. One with the work and energy theorem, which we're going to do first, and then second from a conservation of energy standpoint, which we'll do second. We'll do both those solutions. We know that those two solutions are largely similar to one another, and you don't do both, but you can kind of choose for a particular perspective which one you want. So in the last problem, we found the acceleration of object one, and that's a good thing to do when if the problem asks, obviously it's a good thing to do if that's what the problem asks, but that methodology we used with using torques and accelerations and Newton's second law is a good thing to do if you're being asked about the forces, like find the tension, which you did in the problem that you did last night, or find the acceleration. But what happens if the question is something like, okay, after object one has moved down a distance of d, how fast is it going? Right? So if that's the sort of question that you're being asked about speeds or positions, it's a good idea to use energy. If you're being asked about times, accelerations, and tensions, use your force analysis. So we're going to find out what is VF1 after it has fallen a distance of d. That's our problem. And we're going to start out doing this using the work energy theorem as the reason, as the way. So let's start, as we always do, with the forces. So I still have Fg1, I still have Tp1, here is T1p, here is Tp2, I should have commas, 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 here is Fg2, here is T1p, once again Fgp, and Tp up. Now, we talked once again about the static friction force between the wheel and the rope and between the rope and the wheel. That's going to become important in just a couple of minutes. And remember, we said that the rope does not slip with respect to the pulley. Here's the analysis that we're going to do, or rather in this problem, we'll see the analysis that really makes that super important. So here we go. If I was going to use the work energy theorem, remember my main idea here is that the net work is done is equal to the change in the kinetic energy of the system. And I cannot do individual parts and pieces. I cannot do this just for mass one, just for mass two, just for the pulley. It's got to be some sort of holistic perspective if I want to do this the right way. So if we're looking about work, the first thing I'm going to do is I just want to eliminate a couple of things so that we don't have to deal with them. Nothing moves along this axis. Those are just not going to do work. They're not going to come up in our work net equation. So if we're going to write that, I would have the work done by gravity on mass one just kind of going up, plus the work done by tension P1, plus the work done by tension 1 on P, plus the work done by tension 2 on P, plus the work done by the tension on P on 2, plus the work done by gravity on 2, right? And that's going to be this side. I'm going to leave a little bit of space there for a reason we'll talk about in just a moment, is equal to the change in kinetic energy. And so that's going to be the kinetic energy finally of object 1, plus the kinetic energy finally of object 2, plus the kinetic energy finally of the pulley, minus the kinetic energy initially of 1, plus the kinetic energy initially 2, plus the kinetic energy initially of the pulley. Now we're going to alter these terms in just a bit after we have a bit of a discussion. So, thing one, let's finally deal with this static friction. Right? So I have static friction acting between the pulley and the rope and the rope and the pulley. So why am I not doing a work term in places there? Well, if you think about it, because the rope does not slip with respect to the pulley, there's no displacement going on there. So Or another way to visualize it is even if there is displacement, there's displacement that is identical in both directions, i.e. the work done by the force of static friction on the pulley is going to be equal in magnitude and opposite in sign to the work done by the static friction on the rope, because they would have the same magnitude as Newton's third law pairs, the same displacement if they're not moving with respect to each other, but one would have a cosine of 0 and the other would have a cosine of 180. So what is it that that static frictional force does? The static friction between the pulley and the rope, what that acts as, it's the mechanism of energy transfer between the masses and the pulley. And it's going to be the reason why the pulley here is going to gain kinetic energy as these things are changing in gravitational potential energy, right? So that's going to be the reason why. So we can either think of it as a Newton's third law reaction, and because there's no slippage, those two distances are the same, but one has positive, one has negative, therefore we're not going to consider it, or just simply as a mechanism of energy transfer. So now let's go down to our next conversation, and that's kinetic energy. So what are we talking about kinetic energy? Well, remember, there's two types of kinetic energy. One we'll call KET, which is translational kinetic energy, and that is about the velocity or the speed of the center of mass. If the center of mass is translating, something has translational kinetic energy. But if I want to talk about the rotation of an object, we showed that I could talk about holistically rather than talking about each individual point on this pulley by doing 1/2 I omega squared. And that's the rotational kinetic energy. So down here, that's a translational, that's a translational, that's a rotational, this would be a translational, this would be a translational, and this would be rotational. Okay, so let's make this a lot easier now, because let's say that the system starts at rest. So V1I is equal to V2I is equal to 0, and omega initial is equal to 0. So I'm going to be able to zero out all these terms. Next, let's get rid of our Newton's third law pairs. That's a Newton's third law pair. We've demonstrated in the past that these works together go to 0 because one's going to be positive, one's going to be negative, but since these two forces are equal, and if this moves down so much, then this part of the rope moves down the same amount. There you go. I can once again zero these out. So I'm just left with these terms. So plugging in, what does that leave us? That leaves us with the work done by gravity. So that's going to be FG1, right, times its displacement, which here is d, cosine of the angle between the force and the displacement, which is 0, plus FG2. Now, if this goes down d, that goes up d, because these are at the same radius, right? And the rope here is going to just move a certain amount that moves this part of the rope around a certain amount around that same circumference, and so that's d. So as long as these two ropes are the same rope and are attached at the same radius, you might be like, when does that not happen? Well, we'll see that in a little bit in a different problem. That's going to make our lives a lot easier. But this one is going to be cosine of, let's take a look here. So that's the direction that d goes. That's what FG2 is, so that's cosine 180. And then that's going to equal 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared, and then plus 1/2 I, and that's I of the pulley, omega squared. So now we need to know a couple of things. One, I need to know where the axis of rotation is if I'm going to find I. Boom. Two, I need to know what the pulley is shaped like. Let's say it's a disc. And so that means I COM of a pulley here would be 1/2 m of the disc, which is the pulley, times the radius of the pulley, which we'll just call capital R again for sake of ease. So once again, how many knowns, how many unknowns? Well, I'm going to know this, mass 1, mass 2. I'm going to know this. And now the question is I have 3 unknowns again. So this is where we go back to that earlier analysis that we talked about in the previous problem, where we can exploit something about omega, right? So here looking at the pulley, if I'm talking about this point on the pulley has a certain tangential velocity. This point on the pulley also has a certain tangential velocity. So if these 2 points are at equal r, because v tangential is equal to omega r, the tangential velocity of this point is equal to the tangential, well, the tangential speed of this point is equal to the tangential speed of this point. And since this is attached along a rope like this, the tangential speed of mass 1 is equal to this tangential speed as long as the 2 r's are the same, because we know omega is the same for all points. So because omega is the same and r1 is equal to r2, therefore v1 is equal to v2. And that's going to simplify our analysis. So coming up to this line here now, I can now write the next line in the analysis, which would be m1g d cosine of 0 degrees is 1 plus m2g d, and this becomes -1, is equal to 1/2 mass 1 v, and we'll just call v1, v2, just equal to v final, because it's just simpler that way. So v final squared plus 1/2 m2 v final squared plus 1/2, we know the pulley's I here is 1/2 m of the pulley r, capital R squared. And what's omega? Well, looking here then, I can put that in terms of either v1 or v2 because I happen to know that, because I know that v1, or rather r1, is equal to just capital R here. So this becomes just v1 over capital R quantity squared, and that's going to cause my r's to cancel out there. So when I'm coming back down to this next step then, I've got m1gd minus m2gd is equal to 1, let's just factor out a whole bunch of stuff here. I could factor out a 1/2 and m1 plus, I guess a factor, actually, hold on a second. I could factor out a 1/2, and then I would have m1 plus m2 plus 1/2 mp, and then just v, that'd be v final here, v final squared. So if I'm looking for what v final squared is, let's just do a little rearrangement here and solve for vf. So it'd be 2gd m1 minus m2 all over, I multiply that across, m1 plus m2 plus 1/2 mass of the pulley, square root of quantity, plus or minus, get rid of that because I'm looking for a speed, and that's what VF is using the work energy theorem. So pretty straightforward in terms of other analysis. The only new things here are just having to account for this term. And so that's how I would do the Atwood's machine using a work energy theorem. So now let's just quickly do that using conservation of energy. So here we go. I'm going to just draw the system here. And what I know here is that sometime later, what's going to happen is that mass 1 is going to go down and mass 2 is going to go up. Okay? And so if it's a conservation of energy, what I want to do is label my important points. So I'm going to call this point A and point B. Notice I've lined them up next to each other. We talked about in conservation of energy problems when you're doing it with systems that you want to actually draw 2 separate pictures so you can do some stuff with the UG is equal to 0 line rather than talking about one mass moving around. So what I'm going to do here is I'm just going to call this UG is equal to 0. Now notice here I should acknowledge the fact that I'm going to make this UG for the pulley is equal to 0. Therefore, since it never changes, it's not going to come into play with my problem. So I should just call this 1, 2 just to be clear. So then if I'm writing total energy statements, I would say here that the total energy at position A is exactly equal to 0. It has no kinetic energy, nothing's moving. Has no potential energy. Everything's at the UG is equal to 0 lines. So then EB would be UG1 plus UG2 plus kinetic energy 1 translational final plus kinetic energy 2 translational final plus kinetic energy of the pulley rotational final. Okay? And we're going to largely get the same result as we'll find. Sometimes people think this is cleaner. So here's the big trick here. EA is equal to EB because the work done by non-conservative force is equal to 0. And you might say, hold on a second, but what about the friction here? Well, as long as it's static friction, that static friction here, remember, is going to act as the mechanism of energy transfer between these masses and this. It's not removing energy from the system. It's actually the reason why this form of energy increases, right? So it's not doing non-conservative work in a weird way. Now, if you want to think about it, we could go back to our earlier argument with the two works canceling out as well. But we do need to recognize that static friction has a role in this problem in transferring energy between the different forms. Okay, so now let's write this out. 0 is equal to, well, this is M1G and then Y1. Now, we said that this goes down, so that would be Y1, that'd be a negative D. Right? Because remember, with gravitational potential energy, mgy, you don't get to choose. Down is negative below the UG is equal to 0 line, and above it is positive. That's part of its definition. Plus m2gd plus 1/2 m1 v final 1 squared plus 1/2 m2 v final 2 squared plus 1/2 I omega squared of the pulley. And I think you can see that this is pretty much identical to the term that we had, bringing it back to right here. You can see that the signs are flip-flop because here they're on the same side as the kinetic energy terms. But if I move them over, I get that. I'm not redoing the algebra just because it comes out to the same way. The question is just, how do you prefer to do the setup with these problems? That is entirely your choice. So we have looked at the problem of the Atwood's machine from a torque and acceleration perspective. We looked at it from an energy perspective. And my thought here is that just it depends on what the problem is asking about how you go about it. And depends on what's given to see which methodology is good. Tomorrow's video, all I'm going to do is I'm going to just do problem 45 in the textbook out for you, which actually asks you to do the same problem once using a torque and acceleration perspective and one using an energy perspective, so we can see more examples of this.